Hey, welcome back. This is Scott and my YouTube channel on data science and analytics topics, open source software, commercial software, and more. So today we're talking about a commercial platform called Statistica. This is a little series we're doing on clustering or non-supervised machine learning. And I've done a couple of these, and this is the third. And we're going to be talking about the EM algorithm for clustering. So EM is expectation maximization. This is going to be very much a hands-on how-to, but if you're familiar with maximum likelihood estimation, essentially that's what the EM is about. It's about maximizing a parametric distribution based upon the data. And the expectation of theta given the data, is my professor used to say. Okay, so I'm going to pick up where we had last time. We were using this marketing data, which is household data. So each row is an observation from a household, and most of it is categorical data, marital status, age, education, occupation. How long that they stayed in this residence, whether it's dual income or non, etc. And so what we want to do is we want to figure out how these different observations would cluster together. So we have to put together build a clustering structure, and then we can look at how the individuals fit into those clusters. So the first thing that I'm going to do is I am going to go up here and I'm going to type in cluster. Actually, before I do that, notice let me just show you something real quick. So I didn't get any of the results that I wanted, and that's because I don't have an open workflow. So Statistica is very much concept driven, and so I don't have a workflow, so it's going to try to point me in a certain direction. But if I open up a workflow, I'll get a different result. So let me click on that. We've talked about that before, but just so that you know. Anyway, now if I type in clustering up here in the feature finder, I get a broader set of options. And so I get everything from neural nets to the k-means that we talked about last time in the tree that we talked about time before that. But today we're going to be talking about generalized expectation maximization, or EM algorithm. So the first thing I'm going to do is I'm going to set up my variables, and I'm going to set up, I'll just select all of these categorical variables as inputs. If you didn't notice how I did that, I double clicked on the upstream node. That's what you need to do with these SVB nodes. You need to click on the upstream node, and then you get this option to set your variables. That's an important little piece. On the regular nodes, the non-SVB nodes, you don't have to do that. It's actually, you can set your variables inside the nodes. So now, clicking on this generalized EM algorithm, and one of the nice things about this algorithm is I can do v-fold cross-validation. If I do v-cross-validation, it doesn't really matter what I set my numbers of clusters. Last time we determined the number of clusters, but this algorithm will actually do v-fold, and what it's going to do is it's going to do a 10-fold cross-validation. If you want to, you can set a seed so that you'll get the same result every time, or you can set it randomly. It's going to run from 2 to, you probably don't even need 25. Let's just say 2 to 10 clusters. In other words, it's going to actually generate 9 different models, 2 to 10, and then it's going to basically determine the cutoff for 5% decrease. And then I could set my distributions and deployment. Actually, I will set deployment. I'm going to actually generate some PMML code that I could use in another model. So I'm going to do that, and then I'm going to run, and should be getting some results here in just a second. And now I have So let's look at a few of these results. Here, this is the report document, the upper right of the node, and it just says that I ran the EM. I used case-wise deletion, 10-fold, defold, the number of training cases, the log likelihood for the training model, and actually the number of clusters that it determined. Remember, we put 4 in. It determined that 2 is the maximum, the best. And here's the prior probabilities for the 2 different clusters, and some other stuff, and even my PMML, which I could take and save off. But really what I want to get at is I want to get at this downstream document right here, because what it gives me is it gives me the input variables that I used, but then it determined which cluster each one of these observations is going into and the probability associated with it. So you can see here that for the first few cases, it really fit well, and with very high probability assigned those cases. And then, but for some of these, the probability is a little bit lower. So what does that mean? It is not a very good fit. Again, we talked about anomalies last time. And so if one thing I could do, if I wanted to visualize this, I could go up and I could grab a graph. Let's just do a simple histogram off of this. I'm going to set that probability as my variable, and let me just create this histogram. And what we see here is that, yeah, it assigns a big chunk of the observations really, really well. And then it tails off. And some of these observations, it didn't fit very well. Those could be anomalous because those are almost like special cases. So unlike last time, let me just build this out a little more, give you an idea of what you can do with this. One of the things that I can do is I can create a rule. So if I go into the data and the rules builder, you could use transformations as well, but I'll use the rules builder, and I'll say that I want to go ahead and take all my variables I have, but I also want, what I want to do is I want to add a new variable. So I'll use variable equal formula, and I'll call this anomaly. And then I'll say if and only if, and we say that probability is less than a cutoff that we specify, let's say 0.75, then we'll call that yes, if this is an anomaly, it didn't assign it well. Otherwise, we'll say no, and that'll be our formula. But let's recognize, all right. Excuse me. I need to cough. I'm sorry, I had to mute myself. Okay, so this is a formula to create a new variable. Suffering from a cold. Apologize for that. So now if I run this rules, now I get the same data that I had last time, but I also get this, actually I get 2, I don't need this. This is just an error trapping function. But I also get this anomaly, and note here that this row, this household, was identified as kind of an anomalous household. It looks different than all of the other data, essentially, is what I'm saying there. And what I can do there is I can look at, let's just visualize it real quick too. We can create another histogram, and I'll look at this flag. Let's look at the distribution of the flag for anomaly and what it looks like. And sure enough, here's a distribution. Most of these look like they're okay, but then there's a few of these anomalies. And what can I do there? Well, from here, now that I have a target, I've identified a target, I've created the target, and I can do all kinds of things from here. I can build machine learning predictive models. So if I wanted to build, say, a classification shade model, I go in here. My dependent variable is now that anomaly flag that I just created, and I can use my categorical input set, and I can do all kinds of things. I can build all kinds of flows from here. And, you know, obviously I should, if I'm going to want to make sure that I'm not overtraining, et cetera, I would build out a test set, a validation set of some sort and look at it. But, and I know this is really small, but one of the things that I could do here is just look at what tends to bubble from the top. So the first split, if I look at the no's versus the yeses, the first split is household status. And then I move on the right to age, whether it's dual income or the marital status. And I can basically break this down into rules, which are tree, you know, basically a decision rule. And I will look for purity to try to separate those anomalies versus non-anomalies. And I can do all kinds of things. Here's the here's the predictor importance. So age is actually the highest, and this is normalized. So at 100, age is the biggest, and then household status and dual income, et cetera. So pretty cool stuff. We'll quit there. I've got several different models out there for you to look at as far as machine learning goes, but this is an extension from a non-supervised into a supervised way. And again, I'll do something specifically on anomaly detection, a little more deeper, maybe a little longer, but I want to keep this one short. So I will do another one on clustering next time. See you there.